So, we're continuing our sort of introduction to electrostatics. And so, generally the goal in electrostatics is to determine what the electrostatic potential is, or the electric field, given some charge distribution, or some conditions on boundaries, which we'll talk about today. Okay, but I just wanted to remind you something that Manny actually calls Steve, but the triangle of connections between our different objects that exist, and there's sort of different strategies for connecting. Given one of these others, how do you get to the other? Okay, just want to quickly remind you of that. So, for example, if I gave you the electric field and I said, what is the charge density everywhere in space, how would you find it? Well, the integral isn't going to give me what the charge density is at some point in space. So my goal is to say, what is, given T at some point in space, what is the charge density? I could go that way, I could do that. But there's a sort of a straightforward way. What is the relationship? Well, there's Gauss's law, but the differential form of Gauss's law, right? So we know that the divergence of E is 4 pi rho. So we just have to find what the local divergence is, and that by 4 pi, and that gives us rho. So the divergence of E determines rho. If I was given rho and I wanted to find T, well, there's different choices to do that. If I have symmetry that allows me to do this, okay, this is not always true, okay? The flux integral, I can't just bring this outside the integral unless it's a constant over the surface, right? When it's true that the electric field is, its magnitude is, or in its direction are such that E dot, the normal, is the same at every point on the surface, then I can factor it out outside the integral, and that gives me a way of finding the electric field along the normal. And by symmetry, I need to know something about what direction the electric field is pointing in, right? So that if I have that, use it. But often I'd have to go the other direction. I'd need to find the potential. It's much easier to directly integrate and find. How would I do that? If I was giving you the charge density, I wanted to know what the potential is, how would I find it?
Divergence. The Green's function.
I'm listening.
Green's function?
Yeah, Green's function, which effectively is saying, so we know that the potential is just Q over R, okay? We should remember simple things, too, because it gets so confusing, there's all this sophistication. And that is just basically saying I integrate over the charge density, the distance from the charge to the point of observation, which, as we said, is the Green's function solution, but that's really Q over R, right? So I can integrate that, and then I can find, and if I wanted to find the electric field given potential, how do I do that?
Take the gradient.
Exactly, yeah. So these are things that I really want you to sort of just be ready with, right? So be thinking about it the other way around. Of course, if I was given the electric field and I wanted to find the potential, how would I do that? I take the line integral, right? So the potential at some position is the minus going from ground up to x of E dot U, etc. Okay. Okay. Now, one other thing we talked about briefly last time, but I just wanted to emphasize, is the notion of boundary conditions. On the electric field. Okay, so if I have some surface, okay, come out of the board here. It could be an imagined surface or the surface of some Kuzelweiser piece of material, right? And I have some electric field on one side of the surface and some electric field on the other side of the surface. And I want to know the continuity of the electric field or discontinuity of the electric field across the surface. Well, one thing I can do is use Gauss's law even without the symmetry if I'm interested in a local point, okay? So if I want to say right here at this point, how does the electric field change across the surface? Well, one thing I can do is I can make a little Gaussian pillbox that straddles the surface, and there's a normal to it on both directions. And as I take the limit as the height of the pillbox goes to 0, then the label of the can, the side of the pillbox, contributes nothing to the flux as I take that limit, but I compress it down so it just straddles the surface, right? And so then the only contribution is the flux going through the cap on this side and the flux on the cap going on that side, okay? And so what that would tell me is that the flux through this pillbox, it would be equal to whatever the little area is times n dot E1, and then this is in the minus n direction, so it's minus n dot E2, is equal to the charge enclosed in that little pillbox. Okay? And so what this says is n dot E1 minus E2 is equal to, times 4 pi. Times the local surface charge density at the point where the pillbox is. Okay, so what this tells me is that there is a discontinuity. The component of the electric field that is normal to the surface will be discontinuous if there is surface charge density, if there is a charge density that's concentrated on the surface. We'll see examples of that today. Okay? We saw examples of that last week when we looked at, for example, a plane of charge, and we saw that there was a discontinuity in the electric field on one side or the other of that plane, right? Similarly, I can say, well, here's my surface, there's my electric field, on E1 on this side and E2 on this side, whatever it is. And now, instead of taking a Gaussian surface, I'm going to take a closed contour, okay, that straddles the surface. And I'm going to take the limit that the this height of this contour shrinks to 0, so that these two contours just straddle exactly the surface, in which case I can look at the tangential direction, which is the direction tangential to the surface. So I'm taking my contour such that one of the legs is along the tangent vector to whatever the surface is, and then take the limit that I bring those two tangent vectors right next to one another. That then tells me, according to the law of electrostatic that I have an irrotational field, that the tangential component E1 minus E2 has to be equal to 0. The component along the normal does not contribute as I shrink that to 0. So what we have is that the normal component can be discontinuous by surface charge, but the tangential component is continuous. Okay, and that is really can be a useful, well, it's a useful fact, and it can be a useful tool for calculational purposes, as we'll see. Okay? All right. So, right. So, what we've been talking about is calculating the fields, and the fields tell us about forces. The electric field says that the force on a charge Q at position X is equal to the charge times the electric field at that position. Okay? Now, of course, when we're thinking about motion and mechanics, it's also very useful to think about things in terms of potential energy, right? Those are often ways we use to think about dynamical problems, to think about things in terms of energy. So let's just remind us those things of some very basic things. If I wanted to ask, what is the potential energy of a charge in an external field? Well, it's the same concept that we have for gravitational potential energy. If I ask you how much potential energy does a rock have that I brought up from my house on La Luge Trail up to Sandia Crest, the potential energy it has is equal to the work I did to get it there. That's the definition of potential energy, okay? So in a similar spirit to that, I have some electric field that's coming from some other charges, okay? That's the external part, is the E field. And I've got to drag this charge against the force and move it through the field to put it to some point. And that took some work for me to do that, okay? So the work I did, so the potential energy that in going from say, you know, I started out here at position, let's say this is XA, this is XB, and I move the charge somehow from here to here, okay? How much work did I do to do that? Yeah, and the work I do is equal to the force I exert and it's the force I exert to move from XA to XB. That's the definition of the work I do, right? But the force I'm applying is, to do that, I have to counter the force that is being done on me due to, like when I push the rock up, the gravity is pushing down. So the work I do is minus the force of gravity pushing on me when I roll the rock up the hill. Well, I don't roll it, maybe I put it in my backpack, okay? And so this is equal to minus Q E of X dot BL from A to B, and the electric field is minus the gradient of the electrostatic potential. So the potential energy, which we call U, is equal to Q times the line to go from position A to B of the gradient, and that by the fundamental theorem of calculus is that, right? Very basic stuff, but it's good to remind ourselves of it all. And this is why we define this with this minus sign, because it's the work I do. So it's that minus sign is put there to get rid of that other minus sign. And so the change in the potential energy of the charge, moving it from point A to point B, is equal to the change in the electrostatic potential times the charge. So the charge times the electrostatic potential is energy. And so the units of the electrostatic energy is, the units of the electrostatic potential is energy per unit charge. Okay? And in SI, would be equal to volts per coulomb. Okay? I'm sorry, joules per coulomb is a volt. Right? All right. So if I have, if one of my positions is, so I would write U as this relative to ground. So if the position, I'm looking at the potential at some point, when we say it has so many volts, we're saying it has so many volts relative to ground, where XA is a position where the potential is 0, okay? Okay, now that's the notion of how much potential energy does a charge have. In an external field. There's a slightly different concept, but very important concept, which is how much potential energy does it take to assemble a particular charge distribution. So I could start with thinking about initially let's just think about a set of point charges. Let's say I have 3 point charges and they're located somewhere, okay? And how much potential energy did it take to put them at this relative position relative to another? Where say this is charged Q1, this is charge Q2, and this is charge Q3. So I can think about the, how much work I did in order to put these charges here in saying they were all initially separated infinitely far apart where there was no force on them, and then I brought them in from infinity, and I have to, if they're all the same charge, there's a repulsion and there's so much work I have to do in order to squeeze them together to put them there, okay? So these charges are coming in from infinity and coming to these different positions. It's nice to see where infinity is, it's out there somewhere, okay? And I bring them in from infinity to there. And there's then a distance between all of these guys, script D, R12, script D, 32, script D, 31. Okay? So, from this perspective, then, what we see from this is the potential energy here. I can say, oh, well, it's the potential energy of this charge. Well, I can do it one at a time. I bring this guy in. It took no work to push this. There was nobody around to push on me. So it was a freebie. Now I bring in charge 2. And charge 2 has to work against the field of charge 1. And so the potential energy from that would be the charge 2 and the field of charge 1, and that gives me the potential energy that is this, right? That's what we just said, because this is the potential due to charge 1 at position 2, right? So the charge times, this is the potential due to charge 1 at the position of charge 2. And then I bring in charge 3, and it's going to have to act against the force of that, but it's also going to have to act against the force of that, and that will give me that potential. Okay. And so what I can express is if I have a set of point charges, then what I would say is I sum over I, charge I, times all the other potentials Now, to avoid counting, I should divide by 2, right? Otherwise, I'm going to count everything twice. Okay. Yes, sir.
Why don't you have to take into account the amount of work it takes to just keep a charge as you bring in another one?
Against what force?
I guess if you were bringing in charge 2, would that also exert force on the charge 1 and possibly repel it?
Oh, you mean we want to do the second charge?
Yeah.
Right. No, but the point is, it's because we're looking at it I've taken this charge and I've nailed it down, right? Because at the end of the day, they're at these different positions. I don't have to think about this as a sequential thing. I can be doing them all at the same time, but it's just conceptually you say, I did it, I nailed it down. Yeah.
And when it's nailed down, it's going to be exerting that force on our...
On 2.
Exerting the force. And there'll still be a force on 2, but...
There's a force on 2, and the force on 1 is equal to the force on 2. That's fine. They're equal and opposite forces, but the work I do is the work I have to do to push 2 to this position, given Q at that position. Nailed
Oh,
it.
and then if Q isn't moving, then
That's
there's
right.
no work.
That's right. This factor of 2 is very important. It's a little bit different because of the fact that we're looking not just as on an external field, we're looking at the fields of the self field of everything. Except, so let me just rewrite this as sum over I and j not equal to one another, qi, qj, divided by Now, there is a sort of very subtle point here, which is when I brought in the first charge, I said that was a freebie because there was no other forces acting upon it. And that ignored the force that the point charge feels from its own electric field. And that's the whole story. This is a problem in classical electricity and magnetism of the notion of the self-field and how the self-field affects the charge. We ignore that because that would be infinite, because the electric field of a point charge at where it is infinity. And that's an infinity that we really just can't get rid of in classical physics. We can only do that in quantum electrodynamics. Okay, that's a separate story. Okay, so if I wanted to now think about not a discrete set of charges, but a charge density. Smooth as peanut butter. And I wanted to know how much work would I did and what's the potential energy associated with this charge distribution. It's the same idea, but now instead of doing the double sum here, I will do a double integral. And so another way of writing this is what we see here. This object integrated over x prime is the potential associated with this charge distribution, right? Everyone see that? Because let me write it in a slightly different way. Everyone recognize this as the potential associated with that charge distribution at the point of observation, okay? So the potential energy of this charge distribution is equal to this. Notice here, if I rewrite this in an external, this is the external potential associated with other charges, right? So there was some other charges producing this electric field. I asked how much work did I have to do? That's the potential energy. That's equal to the integral over x prime, rho x prime, phi external of x prime. That's the same thing, that's a rho, not an e. That's just integrating this when I have a continuous distribution. Thing to note is this factor of a half. The factor of a half is coming because these are slightly different problems. This problem I said, oh, I'm moving charge density against some other forces. This was all the forces on each other. Okay. Notice when we have the continuum, we don't have these singularities associated with the points. Okay. So this is a nice expression.
So that x is raised to which power on the u equals 1/2 integral d cubed x rho x integral d cubed.
That's a prime.
Oh, okay.
Excuse me. I'm integrating over. This is just a double integral, and I have two. Excuse my sloppy handwriting.
Now,
Is it clear now? Yeah. Mm-hmm.
The half is just that we don't double count, right?
Yeah, it started from this, but at this point there is no counting, so to speak. It's this is a continuum
So
integral.
we don't double count the differential.
Yeah, but it's not quite the same thing. All right, now, there's an important notion, yeah,
Here, there's only a single charge distribution, right?
there's a single charge distribution.
So we're kind of trying to understand its effect on itself, in a way.
Yeah, I mean, so the way you should think about it is, how much work did I have to do to create this charge distribution due to the forces that all the charges exert on each other?
Is there any other way to come with this expression?
That's the definition. The definition is how much work did I have to do to bring this charge distribution together. And we derived it in that way. That's how we got it, because that's the definition. Yes?
How do we enforce I not equal to J inside the double integral?
We don't. There is no more I 9 J. This is just the whole expression. That's just it. Because there's no discrete points here. Now, an important concept that now arises is, where is this potential energy stored? Well, there's one way to think about it, is that this is stored in the field. In other words, when we are moving charges, we are creating some entity, something that we're going to think about as a different kind of stuff that is not the matter, but the field itself, and the field itself could be the entity that has the energy. And we can see that in the following way. Let us use Steve, the triangle, and as we just said, I can re-express the charge density in terms of whatever the local electric field is at that point. Okay? And this is over all space. Okay? Now, yeah.
So if we're saying that the energy is stored in the field, then what about the energy of just a point charge that we didn't do any work on?
Yeah, well, that's a problem, and the answer is infinity.
Okay.
We'll see that in a moment.
Okay.
Yeah. I mean, it's really the idea of, we would start with the sphere and we would say, you know, I'd have to be super Hercules to squeeze the sphere into a point, and it would take me an infinite amount. But Zeus could do it, but I can't. Okay.
Not with that attitude.
That's right. Okay, so, now, a trick of the trade. When you're dealing with integrals that have, one of the guys has a derivative on it, we can always throw the derivative on the other side using something called integration by parts. But the way you learned integration by parts with UDD, DDU, and calculus, whatever, forget it. That's not the way you do integration by parts. The way you do integration by parts is the following thing. You throw the derivative on the other side and put a negative sign. Why is that? So let's just a little aside. Let's say I have an integral that looks like this. Okay? I have the integral of this. I want to do integration by parts. The way I remember it is, I mean, I don't do this, but once I do this once, I'll never do it again. This is equal to the f dx times g plus g times, plus f times dg dx, right? Which means that this is equal to the derivative of the product minus dg dx, right? Which means that this is equal to right? Now this, I could just integrate, and I get FG at A minus FG at B. Okay? So, what this says is that this integral is equal to the same integral, but I threw the derivative on the other side with a minus sign, plus surface terms. That's saying what it is on the boundary, whatever the product of B and G is on the boundary. The difference between what it is on one part of the boundary versus the other. And so when we do integration by parts, that's what we have. We throw the derivative on the other side and we put a minus sign, and then we think about the boundary terms. That's how you think about integration by parts. Okay? So I want to do that here. I want to take this and throw it on the other side. Why do I want to do that? Because then this is going to look like the electric field, because the gradient of the potential is the electric field. So I do the same kind of thing that I just did over here, but with more complicated derivatives, right? So I look at the divergence of this field, and I can use Einstein's summation convention, and it's pretty quick to show that this is equal to phi times the gradient, the divergence of E, plus E dotted into the gradient of phi. Okay? So this then tells me that this is equal to right? That's integration by parts. Okay? Now, what about the surface term here? So this is the integral over a volume of the divergence of a field. What is that equal to by the divergence theorem? Sorry?
On the surface?
It's something about the surface, right? This this is phi times E dot n hat dA by the divergence theorem. But what surface am I talking about? This is the surface that encloses the volume. But the volume is all of space. So this is a surface at infinity. So this, and if this is a localized charge distribution, then the electric field and the potential have to go to 0 at infinity. So this, the surface term, goes to 0 for a localized charge distribution. So for anything that doesn't extend out all the way to infinity, this will be 0. The boundary term is 0. And the gradient is minus the electric field. So what we find is that the potential energy stored in the charge distribution is equal to d cubed x, the magnitude of E squared over 8 pi. Very nice. So what we have found here is that I'll call little u as a function of x is the square of the electric field over 8 pi is the energy density. It's the energy per unit volume. When I integrate over the volume, I get the total energy, the total potential energy stored in the system while I created this charge distribution. That's my picture. nature of creation, okay? Yes?
E is infinity, phi is zero, E is not that.
Sure it is. The electric field falls off like 1 over r squared or 1 over r cubed.
So E infinity, phi is zero.
So is the electric field. Both are 0. Doesn't really matter because the whole integral will be 0. But the electric field falls off with distance, right? So if I have a point charge, it falls off like 1 over the distance squared. If I have a dipole, it falls off like 1 over distance cubed. The electric field has to go to 0 at infinity, but so does the potential. Both are true. Yes?
So I get the electric field falling off as 1 over r squared, but I'm thinking back to Gauss's law. The whole point is that you make your sphere bigger and bigger and bigger, and that integral over the whole sphere always is constant. So I'm a little confused. Like if you send your surface to infinity, like yes, like the field goes to 0, but your sphere also, like the size of your surface area also goes
That's
to
true,
infinity.
but the product of these will always go to 0
Right.
faster than the
So you
that's
do
a very important, you're a good point. If I just had, this could cancel, this would go like r squared, and this would go like, say, 1 over r squared, and then the product of them would not go to 0. So you're right, there's a subtle point that I didn't really explain correctly. It's really the product of these has to go to 0 faster than the area.
Okay. So I guess my question is, you do have to check to make sure that.
Yeah, that is correct, yeah. Yes?
You probably talked about this, but what's the, like, script U or the little u, whatever that is?
Right, this is what so what I'm saying is, let me call this little u. I'm defining that as that integral, okay? So I'm just definition, and what I'm saying is that this, when I integrate over space, I get the potential energy that it took to create that. I'll get your question in one moment. And so the important point here is that through this construction that we did, thinking about the work it took to assemble a charge distribution, we came to this idea, at least mathematically, that the field is a thing. It's a thing that has energy in it. And this is what its energy density is. The square of the field is the energy density. Now you could say that this is a bookkeeping, I mean, who's to say that this is that there's anything real, in the same way that we thought about action at a distance in Coulomb's law. I mean, we could, but as we'll see, it's a very useful construct, and construct we use in thinking about the nature of the stuff in our universe, to think about the field as an entity unto itself that has stuff. Like, I mean, it could have mass, it could have, now of course the photon has 0 mass, but that's another story. But it could have spin, it's just like, it's no different than any other stuff like an electron. And it becomes more poignant when we think about radiation, when the electric fields can kind of fly free and detach themselves from the mother charge and just go off and be completely a separate entity. Yeah, your question.
So the integral that we set to 0 by saying, the electric field and phi,
Yeah.
potential are going to go to 0 infinity.
Yeah.
What about for like an infinite plane of charge?
Yeah, this wouldn't work. This wouldn't work.
So for that,
Because the electric field would be infinite, the electric field is everywhere, true. So this would not, if the field, so we would never, we can still, we can think about limiting cases, right? But this integral only really works if we have a localized charge distribution. Otherwise, the electric field will be infinity. This goes out to infinity. It just doesn't work. It's only true for a localized charge distribution.
So in that case, do you get a energy density that's not E squared?
It's just that we would have to think about how we define the boundary conditions. Okay, good. And let's then talk a little bit more. So anyway, this is a very important result. Yeah.
What's the quantum picture of this?
Oh, we're not going there. We have to get through our work. Let's have a discussion out elsewhere. I know there's lots of great questions. I want to have lots of great discussions, but we got to get stuff done. All right. Quick point here. What if we look at this? What are the units of the electric field thing? Well, they're the square root of energy density in CGS, right? And you can check that that works. I mean, so in CGS, there's a relationship between the units of charge and field and mechanical units. Otherwise, as you might remember, 1 over 4 pi is epsilon naught. So in units you might be more familiar with, you would write this way in SI units. And there's an epsilon naught that lets us know, but who knows what the units of epsilon are? Does anyone know?
That's permittivity?
Yeah.
Well, wouldn't the electric field be volts per meter?
Yes, what's the units of epsilon naught? No one knows. Never mind. I rest my case. Farads per meter is one way of saying it, but that's another. What the hell is a farad? All right. So let's talk. Let's see. Oh gosh. Yeah. All right. More about the question of boundary values. And this is really the subject of most of chapter 2 and 3 in Jackson, which is when most people think about, oh, I had to take Jackson E&M. That's what everyone thinks about and what they hate, most people. And what we're not going to do, not because I want you to like me, but because, if you don't anyway, it's because most of that stuff is kind of, at this point with computers, we would never solve the problems that way. There's just a lot of special functions and infinite series that were, it's like, when I was in high school, we used to solve algebraic equations with log tables. Now, we had calculators, I'm not that old, but they were still teaching people how to interpolate log tables to, yeah, it's fine, I learned some things, it was interesting, but that's not the way you put it in a calculator and you just do it. So all those boundary value problems, anyway. There's some important ideas, and I think you probably still learn them, and you should learn them, and particularly you get in all because of other places. You get it in quantum mechanics, you get it in math methods, 466, so we're going to do other stuff. But let's talk about the ideas. The ideas are important, okay? So to do that, we're going to first start with Green's theorem, from which the Green's function comes more generally, but let's talk about Green's theorem. So Green's theorem says, let's just consider the following thing. So let's consider the divergence of some scalar field. Let's say that's the electrostatic potential. Doesn't really have to be, but this is a mathematical theorem. Times the gradient of some other scalar field. Okay? So that's the kind of thing we just did over there. That's equal to the field phi times the Laplacian of psi plus the gradient of phi dotted into, that comes from just using Einstein's summation convention, you get it instantly, okay? So let's now integrate, let's say we have some finite volume, V, and there's some surface that bounds that volume. Okay, so there's some volume in space. And I want to know what my goal will be to say something about the potential inside this volume only. I don't care what the potential is anywhere outside the volume. I only care what the potential is inside that volume. Sorry. Yeah.
Is there a reason we are writing the gradient dotted into itself instead of just the magnitude of the gradient?
These phi and psi are not, they're not
yeah,
the same function. Yeah. Okay, so let's consider then, given this, let's say that I look at the integral over some dummy variable, d cubed x prime. Is that what I want to do? Yes. Okay, so I'm going to look at the integral over the volume over some d cubed x prime of this guy. And so that's equal to, according to the divergence theorem, the integral over the no, it's not quite what I want. Hold on a second.
You could say it's just.
Oh, yeah, okay, okay.
Satisfactory answer.
Okay, that's where I got confused, sorry. The gradient. Okay, so now it makes sense. That's equal to this vector field dotted into the surface. Okay, that's the divergence theorem. But this is equal to this, which is the integral over x prime psi of x prime, the Laplacian, plus that. Right? Just substituting in that derivative. So those two things are equal. Now, I can just flip the role of these two scalar fields. I'll get the same thing, but with phi and psi flipped. Yeah.
Is that surface integral, is that dA in the x prime or the x system?
It's at the surface, so.
Okay, so I guess it doesn't matter.
Yeah,
And
it's
then
at the
is that-
surface. This is
okay.
at the surface. Yep. Okay, so if I just flip the role, just call psi phi and phi psi, I'll get the same expression, but with phi and psi flipped. And what we see is this thing is symmetric between them, so I can take those two solutions and subtract them. And when I do that, I get the following integrals. What I get in that case is the integral d cubed x prime phi at x prime, the Laplacian of psi at x prime, minus the reverse thing. And that equals the integral over the surface, and I'm going to use a little shorthand notation here. Where I've written that the gradient dn, what I mean by that is n hat dot this. Okay, so I obtained that by just taking the solutions we had, flipping phi and psi and subtracting that. This is known as Green's theorem. Okay, so that's just a mathematical expression. It says nothing about electrostatics or anything else. It's just vector calculus. But now I'm going to say, let this be the electrostatic potential. And let psi of x prime equal the Green's function for some position x. That is to say, I want this function which is parameterized by x, the position of observation, to be the solution to the Poisson equation for a uniform charge. Okay? So, because this is true for any scalar fields, I'm choosing scalar fields that satisfy this. Okay? And when I plug that in, what do I get? Well, the first term is going to have a delta function in it. And right. So this is true. We'll question, what is this? Yeah, this is the Poisson equation, right? And so this is equal to minus 4 pi rho. That's the Poisson equation. So I plug that in over here, and what do I get? The first term gives me a delta function. I can integrate it over that, and I'm going to get 4 pi, minus 4 pi, the potential at position x. And then I'm going to get plus the integral over x prime, the Green's function times that, so that's, let's put this, let's make sure I get all the minus signs and all that correct. That's psi is equal to the Green's function, and this is equal to minus 4 pi rho at x prime, which is equal to the integral of phi times the derivative of the Green's function normal minus the Green's function times the normal derivative of phi integrated over the surface. So, putting that all together, I get the following, and then we'll interpret. This tells me that the potential at position x is equal to the integral of rho of x prime g of x minus x prime minus 1 over 4 pi, the integral over the surface, the potential at the surface, times the normal derivative of the Green's function at the surface, minus the Green's function, times the normal derivative of the potential. And this is the general solution to the Poisson equation or Laplace's equation in a finite volume.
Does it have a name?
No, this
The
is
general
the solution.
Yeah, right.
Now, let's think about it and let's interpret it. Firstly, does this agree with what we already have derived when the surface is at infinity and this is the whole volume? So if the surface goes to infinity and the volume is all space, we want that the potential goes to 0 at infinity. So in that case, this term is 0. And what is the Green's function? 1 over r. 1 over the distance from the point. So in that case, this is equal to this. And we get the solution to Poisson's equation that we've already written down.
Did you forget to write the differential at the end of the surface integral?
I did. So this agrees with what we already had, where we had no surface. But this problem allows us to solve other kinds of problems. There's an important result about uniqueness, the uniqueness of the solution to the Poisson equation. So this equation, remember, is the Poisson equation. If the potential, if the charge density is 0, we call it Laplace's equation. This is not the case when rho is 0. If rho is 0 in the volume, doesn't mean it's 0 everywhere, it just means inside the volume. Then the solution to Laplace's equation is just given by this piece. Okay? So, this solution is unique. Let's quickly prove that. So let's suppose that there were two different solutions. So let's suppose phi 1 and phi 2 are different solutions. And let's look at the difference of them. We want to show that phi of x is 0, capital Phi is 0. Or equivalently, it's a constant. If it's a constant, it doesn't matter, because what we really care about is the field, which is the gradient of the potential, and that's just a matter of shifting around ground, where ground is, okay? So from the Green's theorem over here, we can look at these two different solutions. So from Green's theorem, the integral of capital phi times the Laplacian of phi minus, so I'm going to go back to the original before I did the subtractor-root over here and look at this expression on this board and choose little psi and big psi equal to be the same thing, capital psi. So that's, this goes back to one of the earlier questions about why this wasn't just the magnitude. So now I'm just looking at that, integrated over all space is equal to the surface integral I obtained this expression by looking at this expression and taking little psi equal to, little phi equal to big phi and psi also equal. I could choose those functions anyway I like, and this is a mathematical identity, okay? So if these guys are both solutions to the Poisson equation, then this is true, right? Because del squared this and del squared that are the same thing. So this term vanishes. And this says that the integral over all space is of this thing is equal to minus this. Now, what about this? Well, if they're the same solution, then okay, yeah, okay. Now I understand what I want to say. So, if we have boundary conditions, we're saying that both solutions have to have the same value of the potential and or its normal derivative on the surface. So that means that both this and this, so that what this is true for the given boundary conditions is that it says that this is 0 on the boundary because they have to satisfy the same boundary conditions, and or the normal derivative is 0 on the boundary. Okay? And so either this is 0 or this is 0, or they're both 0, which means this has to be 0 for a fixed boundary condition. So what does that tell me about this? Well, what it says is that since this is an integral of a positive thing over all space, right? This thing is greater than or equal to 0 everywhere because it's the square of a positive number. How in the world does this integral gonna integrate to 0? It must be 0 everywhere, because there's no positive to cancel a negative. So what this tells me is that the gradient of psi 1 has to equal the gradient, of phi 2. Which means that either these guys are equal, or the difference between them is some constant. QED. So QED gets a smiley face with a beard, glasses, and a little bit more hair than I used to have. All right. Very good. Voila. So what we have learned from this proof is that if I specify on the surface of that encloses a volume, everywhere what the electrostatic potential is, or everywhere what its normal derivative is, or some combination, then that fully determines the problem, given whatever charge densities are there. Now, it's a little bit, there's one subtlety here, which is that I can't overspecify the problem. If I specify both the potential and its normal derivative everywhere, then I've overspecified the solution. And there's no solution necessarily that can satisfy both of those things. But I can make a choice. I can choose either what the potential is, or its normal derivative, or at some points I say the potential, at other points I say what the normal derivative is, but at a given point I don't specify both.
Why can't you do both?
Because that will, you can see from this solution that there could be different solutions depending upon which I specify. So they can be inconsistent. And these things have names, so specify phi of x everywhere on surface. I'll call Verge lay boundary conditions. And if I specify the normal derivative everywhere on S, it's called Neumann.
That's how you say that. I never knew how you pronounce that.
There's a lay? Yeah. There's a lay. On peut pas le français, tout simplement.
Dirchlet and Newman's.
Yeah, exactly. Right. So I just said, or just as an example, so here's a kind of classic Jackson problem. We'll talk about something like this next time. I have a conducting sphere. Okay, and let's say that I ground it. You're grounded sphere. All right? And so the potential on the surface of the sphere is 0. Yeah. And now I have some blob of charge out here. And I want to find the potential outside the sphere. Okay? So it's bounded, in this case, by the sphere and infinity. I don't care what the thing is inside. How would I do it? Well, what I can do is, first thing is I find the Green's function associated with a point charge with this conducting sphere that's grounded. So the Green's function is the potential associated with a point charge that is sitting next to at some point. If I know what the potential is associated with the point charge, I can integrate over the charge distribution according to this and then I have to add the surface terms. Now, what happens, as you may remember, we'll talk about this, is that, you know, the electric field lines go normal to this, right? And so we have to find what this field is for the point charge. And once we do that, we can find it for any charge distribution, okay? So the problems of the boundary conditions for Poisson's equation is finding the right potential associated with a point charge with the given boundary conditions. And there are tricks to the trade. There's, you know, orthogonal functions and writing these things in spherical vessels and God knows what. Or, our friend, the method of images, which we'll talk about next. Very good, everybody. Have a good afternoon.
Thanks for the class. So, we're gonna
The sign